Hello friends, welcome to the Organic Chemistry course, and here is our first topic, General Chemistry. Let's look at the contents of our topic. We will start with structure of matter, following periodic table, chemical bonds, and coordination chemistry and metal complexes. Let's start with structure of matter, and we'll talk about atom, isotopes, radiation, and electron shell. All matter, such as solids, liquids, and gases, is composed of atoms. Atom is simply the smallest structural unit of matter, or the smallest part of an element that displays all its qualities is called an atom. Atoms are the basic building blocks of matter. They are extraordinarily small, approximately spherical in shape. Their diameters can vary from 0.1 nanometer to 100 picometer. Therefore, for the structure of matter, it is necessary to first define the atom and look at its properties. Atoms consist of a nucleus surrounded by electrons. For an atom to be uncharged, the opposite charge of the nucleus and shell must be equal. The shell in which the electrons, which we call it electron shell, are located forms the basic volume of the atom. And here you see the root-first model of atom, which the neutrons are depicted as red color. The blue color represents the protons, and the black color surrounding the nuclei are the electrons. The nucleus consists of two separate particles. These are protons and neutrons. Almost equal masses of protons and neutrons builds up the nucleus. Protons are positively charged, while neutrons are uncharged. And the mass of the electrons against the proton is 1 to 2000. This ratio is fixed and is not considered in the calculation of atomic mass unit, AMU, because the electron masses are very small. The mass of the nucleus is used directly in the calculation of the atomic mass unit. And here a question to you: what is the difference between atomic weight or atomic mass, or which one is correct, or what is the difference between weight and mass? And let's try to answer the differences between weight and mass. Weight is defined as the force acting on an object by gravity with the unit of Newton. So this means weight actually is force and defined as Newton. So it's a force weight, and the measurement unit is Newton, while the unit of mass is kilogram. The unit of mass is kilogram and is a quantity related to the amount of energy of matter, and mass is a measure of the inertia of matter. According to Newton's second law of motion, it describes the relationship between the mass of a substance and the amount of a force required to accelerate it. And this law is expressed by the equation F equals mass times acceleration. And here F denotes the force acting on the substance, mass the mass of the substance, and A denotes the acceleration of the substance. Weight is also a force, and if there was no other force acting on matter other than gravity, it can replace the force in the equation, force, weight, as I wrote before. In a non-accelerating item, the value A, which denotes the acceleration, replace gravity. So replace gravity. Therefore, the equation F equals to m times A changes to force weight equals to mass times gravity. Therefore, weight appears as another form of expression of the gravitational force. And the weight of a substance changes depending on the gravitational force of its location in the affecting space, but its mass does not change wherever the substance is. In daily life, mass and weight are often used interchangeably, but we should know that they are different. Then we find the answer to the question in our title. The simplest atom is the hydrogen atom, which is chemically denoted by the symbol H. The nucleus of the hydrogen atom consists of a single proton, and the positive charge plus one positive charge of this proton is balanced by an electron in the electron shell. Thus, when we look at the subatomic particles, protons, neutrons, and electrons, they have symbols, and which hydrogen is used also a symbol of electron. Also here you see the relative electric charge of these particles, mass, and then relative mass, and which you see that the proton and neutron have a relative mass 1 atomic mass unit, but electrons no. The number of the protons in the nucleus of an atom, which has the same number of electrons as in the atomic shell, is defined as the nuclear charge number or the atomic number. It is also called proton number or arrangement number. Atomic number is unique to a particular element. So don't forget, nuclear charge, number of protons, and number of electrons, they are same. Their quantities are same. The sum of the number of protons and neutrons in the nucleus is called atomic mass or nucleon number, but the common term is atomic mass. And here you see an atom showing an illustration having electrons, neutrons, and protons, having six protons and neutrons. Thus, the atomic mass will be 12 as an expression in unit. Atoms with the same number of protons form an element, and atoms with different atomic mass and the same chemical properties are called isotopes. Isotopes of the same element have the same chemical properties because they carry the same number of protons and therefore the same number of electrons. In other words, isotopes have the same number of protons and different number of neutrons. Therefore, the difference between isotopes is due to the number of neutrons. The physical properties of isotopes are different. It is the number of electrons that determines the chemical properties of atoms, because the important determinant of physical properties is mass, and isotopes have different masses. And here you see some examples of isotopes seen in nature, and isotopes of hydrogen, deuterium, and tritium, and maybe the most famous ones, isotopes of carbon, carbon-12 and 13, which are the stable carbon, and carbon-4, radioactive carbon, which also defined as the radiocarbon. And here you see the proton numbers are same. And in parentheses, if we change the proton number, it will be a different element. And the neutron numbers are different. So this is the difference in the isotopes. And here you see the abundance of these carbon forms in nature. Almost 99% of carbon in nature is carbon-12, 1% carbon-13, and trace amounts for carbon-14. And also, oxygen, uranium, and other elements, many of the elements have isotopes. And there are about 275 different isotopes of the 81 stable elements. and there are more than 800 natural and synthetic radioactive isotopes available. A single element in the periodic table can have more than one isotope form, as you see here for the hydrogen and carbon-12. And carbon-12 and the carbon-13 are the stable ones, and carbon-14 is the less stable one, which is radioactive. And carbon-14 has the longest half-life. And carbon-12 is the most common, as I said. And also, atomic mass measurements are made in proportion to itself. The carbon-13 isotope is found at a rate of about 1%, and important information about living things and the Earth is obtained by making measurements in geology, paleoclimatology, paleoceanography sciences. And the radiocarbon isotope is found especially in all organic materials, and the principle of radiocarbon dating is based on the measurement of carbon-14 or radiocarbon. And the scientists who revealed this method were at Libby, awarded with Nobel Chemistry Prize in 1960. And it's so important technique used in archaeology and paleontology. Isotopes can be found naturally, as I said, or they can be formed by giving additional neutrons to the nucleus by radiochemical methods. So this means synthetically obtained isotopes, which we call them actually radioisotopes. The added neutrons are not durable as they disrupt the proton-neutron ratio in the nucleus and cause fragmentation in the nucleus. This phenomenon is called radioactivity, and such isotopes are called radioisotopes. Radioisotopes give off their energy and become stable isotopes. The breakdown of the nucleus of a radioactive atom by spontaneously emitting charged particles or rays is called the radioactive decay. In other words, radioactive decay is the emission of energy in the form of ionizing radiation, and this decay is related to the neutron-proton ratio in the nucleus. Each element has a specific neutron-proton ratio. Ionizing radiation can affect the atoms in living things, so it poses a health risk by damaging tissues and genetic materials. There are three types of energy lost through radioactive decay, and one is alpha particles or alpha rays or alpha radiation. The second one is beta particles or beta ray or beta radiation, and the last one is gamma rays. Let's start with the alpha particles or alpha rays or alpha radiation. And here you see an example of alpha particles of polonium to the lead. It's a form of highly ionizing decay. It is also designated helium, as you see here, helium, because of the bonds of two protons and two neutrons similar to those in the helium nucleus. So this is just a representation. Since alpha particles have atomic number 2 and mass number 4, they can also be considered 4 to 2 helium nuclei. The atomic number of an alpha decaying element is reduced by 2. Look at polonium 84 to lead 82, and the mass number is reduced by 4. The mass of polonium 210 to 206. The sequence in which radionuclides are formed one after the other, starting from a parent nuclide, is called the radioactive family or decay chain. And the decay chain ends with a stable isotope of lead or bismuth. There are three types of natural degradation sequences, and components of the degradation sequence have different types of half-lives or degradation. These are the uranium-radium chain, uran-actinium chain, antiphorium series. So you can try to find more information about this decay chain searching from a web or library. Beta particles or beta ray or beta radiation. And there are two types of beta particles, which one is the negatron emission or electron emission. In your example, to explain it, as you see the carbon releasing beta particles to form nitrogen. It can be thought that it is formed as a result of the transformation of a neutron in the nucleus into a proton. With the beta radiation, the atomic number increases by 1 while the mass number does not change. And to get the atomic number 6 to 7, but atomic mass not change because one of the neutrons transferred to protons, which make the carbon 6, and this is the radiocarbon to the nitrogen. And due to its negatron emission or electron emission, it is depicted as a releasing of one electron particle. The second one is positron emission. Positron emission is the emission from the nucleus of a particle with the same mass as the electron, but with a positive charge. This is what I seen here as a positive charge, and which is formed by the conversion of a proton in the nucleus to a neutron. It's an inverse of the negatron. In other words, look at oxygen, its isotope 15 as an 8 as a proton number. One of the proton turns into the neutron, which makes oxygen to nitrogen by decreasing the proton number by 1. And here, increasing proton number. You see two different pictures, which this one is a picture of a computed tomography, and the right one, positron emission tomography of the liver. And in this patient, there are tumoral developments in the liver, and here the arrows showing the areas, metastatic areas in the liver. And here in the PET, the shining areas are the metastatic areas, and it is much clearer on PET. And PET, or positron emission tomography, is a modern nuclear medical imaging technique. This technique allows some form of molecular imaging of a biological function in the body. And PET images have a higher sensitivity than other imaging techniques. During PET imaging, positively charged beta rays or positron-emitting radiopharmaceuticals are administered to the body, such as fluorodeoxyglucose, 18-fluorodeoxyglucose, or 68 gallium, and these are the common radiopharmaceuticals which that are using in PET, and they emit beta particles when degraded. With a PET scan, an image is obtained that highlights the cancer because the cancer has a higher metabolic rate than the surrounding tissues, as you see here. And the last one is gamma rays. Gamma rays or gamma radiation are electromagnetic radiations with very short wavelengths, similar to X-rays but rich in energy, which are emitted as a result of energy changes in the nucleus. A gamma ray or gamma radiation is a penetrating electromagnetic radiation resulting from the radioactive decay of atomic nuclei. It consists of photons in the highest observed photon energy range. Cosmic rays, nuclear fusion, and experiments are source of gamma rays. And here you see a good illustration showing the effect of alpha particle, beta particle, and gamma rays. An alpha radiation consists of helium nuclei and is easily stopped by a just sheet of paper. However, in beta rays, Beta radiation consists of electrons or positrons is blocked by a thin sheet of aluminum. But to stop gamma radiation, it is necessary to shield with dense materials such as lead, steel, or concentrate. Gamma radiation also has widespread industrial use. For example, non-contact industrial sensors use gamma rays to detect measurement parameters such as level, density, and thickness of substances. Cobalt-60 or cesium-137 isotopes are often used as radiation sources. These types of sensors are used in the mining, food, and paper industries. In addition, gamma rays are used as an alternative to autoclave or chemical sterilization in the sterilization of medical equipment. Importance use of radioisotopes in terms of biochemistry. We use isotopes in research studies, determination of metabolites, diagnosis and treatment of certain diseases, in field of drug development and follow drug metabolism, age detection, and sterilization of foodstuffs and laboratory materials. The emission of radioactive materials such as alpha, beta, gamma, and X-rays is called radiation, and the rays that are exposed affect living systems depending on their intensity and duration. Most affected cells and organs include lymphocytes, erythrocytes, gastrointestinal tract, eyes, anterior pituitary lobe, follicles, egg follicles, and mucous membranes. Cosmic rays, gamma rays, beta particles, any form of alpha particles cause the formation of very reactive ions and even more reactive free radicals as they pass through the cell. These products can disrupt cellular activity, and in some cases, they destroy cells. Radioactivity expresses the number of disintegration of a radioactive source per unit time, and the well-known measurement unit of radiation is the Curie or radioactivity Curie. It is the quantity or mass of radium emanation in equilibrium with 1 gram of radium, but is currently defined as 1 Curie equals to 3.7 times 10 to the power 10 decays per second after more accurate measurements of the activity of radium-226. Today, becquerel is used as the System International unit, and 1 Curie equals to 3.7 times 10 to 10 becquerel, or 1 becquerel equals to 2.7 times 10 to minus 11 Curie. Here you see a photograph of Mary Skłodowska-Curie in her lab, and she was a Polish physicist and chemist who conducted pioneering research on radioactivity. And she was the first woman to win a Nobel Prize, the first person to win twice, and the only woman to win a Nobel Prize in two different sciences: physics in 1903 and chemistry in 1911. And also she was part of the Curie's family 5 Nobel Prize legacy. Continuum electron shell. The trajectory in which an electron of a certain energy level is found around the atomic nucleus with a probability of 90% or more are defined as orbitals. It is possible to represent electrons as a cloud around the nucleus. Where clouds are dense, electrons are more likely to be found, and clouds are called orbitals. We have some definitions, and these are essential, and also it is useful to explain the sometimes confusing concepts of shell, subshell, and the orbital. Shell, it is the path that electrons follow around the nucleus of an atom. These are called energy levels. Because these shells are arranged around the nucleus according to the energy generated by an electron in that shell. And the shell with the lowest energy is closest to the nucleus. The next energy shell is found beyond this layer. In other words, the energy levels of electrons increase from the inside out. The amount of energy is directly proportional to the shell number, and shell numbers are named using letters K, L, M, N, and etc. The shell with the lowest energy level is the K layer. It contains at most 2 times 1 to 2 cause 2 electrons. Each shell, let me erase this one. Each shell consists of one or more subshells, and each subshell consists of one or more atomic orbitals. And these are named according to the angular momentum quantum number. And there are 4 main types of subshells that can be found in a shell. And these are S, P, D, F. And each subshell consists of several orbitals. Orbital is a mathematical function that describes the location and the wave-like behavior of an electron. The term orbital describes the complete motion of an electron, and a subshell consists of orbitals. And the number of orbitals in a subshell is a unique property. An orbital can only hold a maximum of 2 electrons. These electrons are in the same energy level, but differ from each other according to their spin. They always have opposite turns. When electrons are filled into orbitals, they are filled according to Hund's rule. This rule indicates that each orbital in a subshell is singly filled with electrons before any orbital pair bonds. Here in the table, you see the names of the subshell, the number of orbitals in a subshell, and max number of electrons. And these are named according to the angular momentum quantum number. And at the figure also here, you see the schematic representation of shell, subshells, and orbitals. Since the electrons are all negatively charged, they are expected to repel each other, but on the contrary, they attract. This is explained by the spin properties of electrons. Accordingly, electrons revolve both around themselves and around the nucleus. However, since it is in the opposite direction of the spin axis of the neighboring electron around itself, an electromagnetic field is formed, and this force of attraction is more than the force of repulsion. There are some rules we need to know. Which one is the Aufbau rule? Aufbau rule or principle states that in the ground state of an atom or ion, electrons fill subshells of the lowest available energy. Then they fill subshells of higher energy. Therefore, orbitals are filled according to their increasing energy levels. Electrons occupy the lower energy position first, then jump to higher energy levels only when the lower levels are filled. An orbital can have a maximum of 2 electrons. These spins or directions of these electrons must be different, and this is explained by the Pauli exclusion principle. And Hund rules takes into account the placement of electrons in collapsing orbitals of the same subshells. Bonding to s,p,d subshells cannot occur unless and until each orbital is joined by an electron. Electrons repel each other because they are negatively charged. Repulsion can be reduced by separating them and placing them on indifferent degenerate subshells. All subshells with a single electron will spin in the same direction, either clockwise or counterclockwise. While the electrons fill the orbitals with the same energy, they first settle one by one in the same direction, spin direction, and then the number of electrons in the orbitals is doubled with the opposite direction electrons. Bohr's model of an atom. It is the classical model of the atom that describes electrons as a negative charge surrounding the nucleus in point form. And here you see the Bohr atomic model of selenium. And Niels Henrik David Bohr. Niels Bohr presented a model of the atom in 1913 that characterized an atom as a small positively charged nucleus as seen in the figure, surrounding by electrons orbiting the positively charged nucleus in circular orbits comparable to the planets orbiting the Sun in our solar system, with attraction provided by electrostatic forces. The Bohr model of an atom is a popular name for this model. An atomic model of a hydrogen atom was proposed by Niels Bohr. The stability of electrons spinning in orbits was neatly explained by this model. These orbits were called energy shells, as we say, by him. In other words, it is the classical model of the atom that describes electrons as negative charge surrounding the nucleus in point form. And Niels Henrik David Bohr, a Danish physicist, who made fundamental contributions to the understanding of atomic structure and quantum theory, for which he received the Nobel Prize in Physics in 1922. He is also a philosopher and supporter of scientific research. Time for periodic table. Periodic table is a table developed for the classification of elements. Depending on the atomic numbers of the elements in the periodic table, their atomic diameters and electron arrangement differ as their positions change. In its most recently updated form, there are 118 elements in the periodic table. 94 of these elements are natural, 24 are synthetic elements, and 80 elements have at least one stable isotope. 38 of them have radioactive isotopes and decay over time. Iron is the most abundant element in the world by mass. Oxygen is the most common element in the Earth's crust. And here are two scientists, the fathers of the periodic table, Dmitry Ivanovich Mendeleev, a Russian chemist, discovered the periodic law and created the periodic table of elements, and he is best known for formulating the periodic law and creating a forward-thinking version of the periodic table of elements. And Julius Lothar Meyer, a German chemist, he was one of the pioneers in developing the earliest versions of the periodic table of chemical elements. As I said, of the elements in the table, 94 are natural, 24 synthetic, 80 elements have at least one stable, 38 of them have radioactive isotopes, iron most abundant in world by mass, and oxygen is the most common element in the Earth crust. And here you see the updated version of periodic element or current periodic table published by UPAC, International Union of Pure and Applied Chemistry, and the date of this version is 4 May 2022. And here are some elements given in different colors which are related with the living things, and especially in mammals. For the yellow ones we call them macro elements because they exist in macro levels such as milligram, trace elements, and the red ones are possible trace elements, and the trace elements are found in about micro or nano levels. This is why we call them trace elements or micro elements. There were some features that we should know about the periodic trends or periodic properties of elements, which one is the atomic and ion radius. It is the distance between the center of the nucleus and the outermost electrons called valence electrons. Atomic and ion radii decreases from bottom to top within a group and from left to right within a period. So this is the periodic trend of atomic and ion radii. Metallic character. The metallic character of an element is expressed as how easily an atom can lose an electron. And metallic character is related to atomic size, and as atomic size increases, so does metallic character. And metabolic properties decrease from left to right across a period and from bottom to top in a group. So atomic and ion radius and metallic character follow the same periodic trend. Ionization energy. The separation of an electron from an atom is called ionization. The amount of energy required for an ionization is called ionization energy. Ionization energies of elements increase from bottom to top in groups and from left to right in periods. For ionization energy, it is also defined as it is the energy required to remove an electron from a gaseous neutral atom. And electronegativity, the ability of an atom to attract electrons in a covalent bond. And electronegativity increases from left to right across the period and from bottom to top within a group. And this property exists because of the electronic configuration of the atoms. And electronegativity measures the tendency of an atom to attract electrons and form bonds with electrons. And as in the atomic radiant metallic character, ionization energy and electronegativity, including electron affinity, after the next slide, I will define. These follow the same periodic trends. And also for the electronegativity, there are important exceptions to this rule include noble gases, lanthanides, and actinides. Noble gases have a complete valence shell and generally do not attract electrons. And lanthanides and actinides have more complex chemistry that generally does not follow any trend. Therefore, noble gases, lanthanides, and actinides have no electronegativity values. And fluorine is the most electronegative element. And the last trend, electron affinity. It is the accept of an electron from another element thanks to the energy present in that element. In other words, electron affinity is the ability of an atom to accept an electron. And it is highest in halogens, such as fluorine. And ionization energy, electronegative and electron affinity, as you see from left to right, within a period increases, and from bottom to top, these trends are also increasing. And this is why here also the fluorine has the highest electron negativity. And atomic ionized radius and metallic characters from right to left within a period and top to bottom within a group increases or inversely decreases. It's time for chemical bonds, intra and intermolecular bonds. Atoms of many elements bond to other atoms to form new, more complex molecules. The intramolecular force that holds more than one atom or ion together is called a chemical bond. It is through chemical bonds that molecules are formed. Depending on the charge of the nucleus, the distribution of electrons around the nucleus, and the radius of the atoms, different chemical bonds are formed. Compounds formed by combinations of atoms are called molecules, and molecules are formed from chemical bonds. Molecules are electrically uncharged and contain a certain number of many atoms. Molecules are a product other than the atoms that make them up, and it has completely new properties and is held together by interatomic bonds. All the atoms that make up the molecule react, and there is no loss of particles. And here you see the most biochemically significant molecule, undoubtedly water molecule, which is an essential for every living thing, which is also the water molecule is indispensable factor of life. And here you see the covalent bondings between hydrogen and oxygen atoms, the van der Waals sheet or van der Waals radius of each atom, and the degree of this angle. And also due to the lone pairs of oxygen here in the molecule, there are partially negative charge and the positive charge side, which gives the water molecule its dipole character. It is basically the force that holds atoms and molecules together. And the force that holds atoms together to form a molecule is called intramolecular forces. The force that holds more than one molecule together is called intermolecular forces. And both types of forces determine the chemical and physical properties of substances. The main difference between intra and intermolecular forces is that intermolecular forces exist between molecules, while intramolecular forces exist between atoms within a molecule. Don't forget this critical difference between these two forces. And also here a good table which will help you during study, showing the differences and the properties of intramolecular and intermolecular forces. And intra, they are the forces that hold the atoms in a molecule. For intermolecular, they are the forces that hold molecules in a substance. Intramolecular forces are stronger than intermolecular forces. Intermoleculars weaker than intramolecular. They are actually the true chemical bondings because intermolecular forces are attractive forces. Intramolecular forces or the bondings determines the chemical properties of a substance. Intermolecular forces determine the state of matter, such as liquid, solid, and also its physical properties, such as melting and boiling point. And intra ones are the ionic, covalent, and metallic bonds. For the intermoleculars, hydrogen bonds, van der Waals forces, ion dipole interactions, and hydrophobic interaction. And intramolecular forces are responsible for the formation of chemical bonds, and intramolecular interactions occur when two atoms share electrons or donate or gain electrons to or from another atom. And intramolecular forces determine the chemical properties of a substance. And as stated in the issue 2, which I said intramolecular interactions occur when two atoms share electrons or donate gain electrons to or from another atom. I want to say an additional thing, which is, for example, in an ionic bond, which the atoms transfer electrons to each other. And for ionic bonds require at least one electron donor and one electron acceptor. Conversely, atoms with the same electronegativity share electrons by making covalent bonds. So the electronegativity is an important factor in which type of bonding occur between two different or two same atoms. So same or similar electronegativity. Covalent bonding, if there is a gap between electronegativity, especially above 2, the atoms tend to link with ionic bondings. And the metallic bonds are also classified as a type of intramolecular bondings, which they are different actually. Let's start with the ionic bonding, the bonding resulting from the electrostatic attraction between positively and negatively charged ions formed as a result of one or more electrons completely leaving one atom and passing to another atom, which is also called electrocovalent bonding, or we call it ionic bonding. And here it's a kind of attraction, attraction between ions of opposite polarity or opposite charge. And ionic bonding is also an ion-ion interaction. Yes, the octet rule is important because atoms do not have the electron arrangement of noble gases react to achieve it. It is customary for elements to bring the number of electrons in their final orbits to 8 when forming compounds to make them like those of noble gases. And here you see the carbon dioxide surrounded by 8 electrons relative to all atoms. When two atoms come side by side, the electrons come under the influence of the nuclei and electrons of both atoms. At the end of these interactions, the electrons are rearranged in accordance with the octet rule. An octet rule is defined as the realizing force of an ion formation. Electron transport is called electron transfer. The stronger the electron donor and acceptor, the easier the electron transfer takes place. Think about the sodium chloride. Sodium acts as an electron donor, and while the chlorine atom is an electron acceptor. And the magnitude of the electronegativity determines the quality of the acceptor. The smaller the electronegativity, the higher the donor quality of the element. Therefore, the difference in electronegativity between metals on the left of the periodic table and nonmetals on the right is very high, and the ionic reaction takes place easily. Ionic bonding occurs in two stages, actually. The first stage, the ions attract each other according to the basic rules of electrostatics. And in the first stage, cations and anions occur, as you see here, the sodium cation and the chlorine anion. And also, as seen in the second stage, as seen in the reaction formula, ion bonds are formed between two atoms with a very large electronegativity difference. And the strength of the bond formation is electrostatic, and in solid form, typically creates a crystalline structure. And also another diagram showing the formation of ionic bonding between sodium atom and the chlorine atom, with sodium has one electron in its outermost shell and chlorine has, when you count, 7 electrons. It is easiest for sodium to lose an electron to form a +1 ion, a cation, and for chlorine to gain an electron to form a -1 ion, an anion. If sodium can transfer its spare electron to chlorine, as shown in here, both atoms will fully satisfy the outer shell requirements and an ionic bond will form. And here, these are some medically important ions, and as you see, some has a positive charge and some has negative charge, which means that we have cations and anions. Covalent bonding. Bonds formed by the joint use of electrons or sharing of electrons by both atoms are called covalent bonds. A covalent bond results from the sharing of electrons between two nuclei. This type of bond occurs between two atoms of the same element or between closely related elements in the periodic table. And this bond forms primarily between nonmetals, but can also be observed between nonmetals and metals. Covalent bonds are most likely to form if the atoms have similar electronegativity, same affinity for electrons. Since both atoms have the same affinity for electrons and do not tend to give them away, they share electrons to obtain an octet configuration and become more stable. And covalent bonds are divided into two as polar and nonpolar. When atoms with different electronegativities form a covalent bond, their electrons are not shared equally between the two atoms, and as a result, the shared electrons will be closer to the atom with higher electronegativity, which will share it unequally. A polar covalent bond causes the molecule to have slightly positive, the side containing the atom with lower electronegativity, and slightly negative, the side containing the atom with higher electronegativity, because the shared electrons are displaced towards the atom. Therefore, as a result of polar covalent bonds, the covalent compounds formed will have an electrostatic potential, and this potential makes the resulting molecule slightly polar, allowing it to form weak bonds, actually weak intermolecular interactions with other polar molecules. The atom with higher electronegativity, as I said, has more attraction, so it attracts more electron pairs to itself, and the polar covalent bond is formed. And here you see the famous and most important molecule of the life, water. And the intramolecular forces that make up the water molecule give rise to the polar covalent bond. As you see here in the outer shell of oxygen, there are two lone pairs. Therefore, it has a dipole character or bipolar property. And the oxygen side is negative and the hydrogen side is positive. Covalent bonds formed by atoms with equal or very close electronegativity, we call them non-polar covalent bondings. And both atoms attract electrons to the same or about the extent. And here you see an example of hydrogen gas, and the two hydrogen molecules share each electron, as there is no any lone pair, so that there is no a polar character or no charge. Thus we call it nonpolar covalent bonding. And the atoms share their electrons equally. Another important element here, the methane, it's a natural gas, it's an hydrocarbon, and carbon forms four covalent bonding with four hydrogen molecules, and due to there is no any lone pair, thus the molecule is non-polar. So the bonds between carbon and hydrogens are all non-polar. And here a good table summarizing the features and also the differences of ionic bonded compound and covalent bond compound or covalent bonded compound. It happens in ionic bond, as I said before, metal and a non-metal, or it's a kind of electrostatic attraction between two oppositely charged ions. And in covalent bonding, it's an sharing of electron pairs between atoms. And non-metal ions are stronger than metal ions, thus they easily take electrons from the metal. Two opposite ions attract each other and ionic bond is formed. It happens between two nonmetals with similar electronegativity. So the difference in electronegativity determines the fate of type of bondings. In ionic bonding, electron orbitals are separated. In covalent overlap, there are positive negative charges in ionic. In covalent, no, that's high polarity, low polarity, strong chemical bonds and weak chemical bonds. And also, the Greek letters are used as prefixes in nomenclature. They are named with the Roman numerals. the ionic bonding compound solid at room temperature. For the covalent bond components, it varies. They are hard or brittle for ionic inorganic compounds. They are relatively soft for covalent compounds. They are electrically reactive. They do not normally conduct electricity. For ionic compounds, they have high melting and boiling points. In covalent compounds, they have low melting and boiling points. For ionic compounds, there is a high attraction between particles. There is a weak attraction between particles. And pay attention, the star I put for the strength of the bondings, as I said, for the ionic compounds, and are strong, and the covalent compounds are weak. Actually, the strength of the bond formed can be measured by the amount of energy required to break the bond. For example, to break the ionic bonding of sodium chloride, 788 kilojoule per mole is required, while to break the ionic bond of another ionically bonded compound, sodium iodide, 682 kilojoule per mole is required. So there's a difference. So the energy required to break the bond is energy bond depends on the type of depends on the elements that form the ionic bonding. While 348 kilojoule per mole is required to break a single covalent bond formed by two carbon or single carbon-carbon bond, but for the double bond between two carbon atoms, 614 kilojoule per mole is required. And for the carbon-carbon triple bond, 839 kilojoule per mole is required to break the triple covalent bond. And when we compare the triple carbon bond with the sodium chloride, it is stronger than the sodium chloride. Therefore, the atoms between which ionic and or covalent bonds are formed should be considered when making comparison. However, it should be clear that these two types of bonds are stronger than intermolecular interactions. And for the details of metallic bonds, please check or please visit my website BiyokimyaVET for further information about metallic bondings. Time for intermolecular forces or interactions. The forces that hold molecules together are often called intermolecular forces or interactions. And here look at the difference in the intra forces or intramoleculars. They hold together the atoms to form molecules. Here we have the molecules and different molecules interact. Thus, intermolecular forces are the attractive forces that exist between molecules. The energy required to separate or break apart molecules is much smaller than the energy of a typical ionic or covalent bondings. And however, intermolecular forces play important roles in determining the properties of a substance. And these forces are particularly important in terms of how molecules interact and form biological organisms and even life. And the first one is the hydrogen bonding. And hydrogen bonds are intermolecular interactions in which one type of a special dipole-dipole attraction occurs. And they are formed when a hydrogen atom bonded to a strongly electronegative atom is located near another electronegative atom with only one electron pair. Actually, this is also the rule. It is the strongest of the intermolecular interaction, but don't forget it is weaker than ionic and covalent bonds. In hydrogen bonding, a hydrogen atom is between three electronegative atoms such as oxygen, nitrogen, and fluorine, and is bound to one of them by covalent bonding and to the other by electrostatic attraction. So this is the pattern of hydrogen bonding. And hydrogen bonds are strongest when the three atoms forming the bond are in a straight line. Hydrogen bonds are extremely important in revealing the structure of proteins and nucleic acids. For example, the strands forming the famous double helix of DNA are held together by hydrogen bonds, or the hydrogen bonds formed between amino acids are important for peptide chains to acquire their characteristic molecular shapes, especially the secondary structures. Among the strongest hydrogen bonds are here the dots depict the hydrogen bonding or electrostatic attraction, and this hyphen depicts the covalent bonds of fluorine to hydrogen fluorine, oxygen, hydrogen oxygen covalent bonding, and etc. Certain substances such as water, hydrogen fluoride, and ammonia form hydrogen bonds that affect the properties of the substance, such as melting point, boiling point, and the solubility. Other compounds containing hydroxyl group and amino groups also form hydrogen bonds. The molecules of many organic compounds, such as alcohols, acids, amines, and amino acids, contain these groups, and therefore hydrogen bonding is extremely important from a biological point of view. And here you see the major hydrogen bonds found in important biomolecules, and as you realize, many of them present in proteins and nucleic acid structures, and also here between motor molecules. Another diagram here showing the hydrogen bonds between water molecules. So the hydrogen side of a water molecule interact with the oxygen side of another water molecule here, and also continue here with another hydrogen bonds. Hydrogen bonds play a very important role in the formation of the molecular structures of large molecules, and also they cause the melting and boiling points of compounds to rise, because hydrogen bonds can form not only between molecules but also within molecules. Hydrogen bonds are also important for the composition of a drug and how it interacts in the body. Specifically, if a drug acts on a specific target molecule, it must bind to the molecule in some way to change its function. And at that point, hydrogen bonds play a role in this binding. And hydrogen bonds also play a key role in enzyme-substrate interactions. Without hydrogen bonds between motor molecules, life on Earth is impossible. The physical properties gained by hydrogen bonds between motor molecules are indispensable for life. Hydrogen bonds increase the boiling point and the heat of vaporization of water. Vanderwaals forces or interaction. Vanderwaals forces are a general term used to describe the attraction of intermolecular forces between molecules. And they are the weakest interactions among intermolecular forces. However, with a large number of van der Waals forces interacting between two substances, the interaction can be very strong in total, which is important in biomolecules. And there are two types of van der Waals forces: weak London dispersion forces and the stronger dipole-dipole interactions, or van der Waals forces interactions. Interactions between ions, dipoles, and excited dipoles are responsible for many properties of molecules, such as deviations from ideal gas behavior in the vapor state and condensation of gases into liquid or solid states. In general, stronger interactions allow solid and liquid states to remain at higher temperature. However, apolar molecules show intermolecular interactions that we cannot describe as simple electrostatic attractions. These interactions are commonly called dispersion forces. The unequal sharing of electrons causes rapid polarization and at the same time counterpolarization of the electron cloud, forming short-lived dipoles as seen in the aviation for neon. This dipole interacts with the electron clouds of neighboring molecules, forming more dipoles, and the attractive interaction of this dipole is called London dispersion forces. London dispersion forces are very weak interactions caused by the momentary changes electron density in a molecule as shown in the animation. And van der Waals forces are the only attractive forces present in nonpolar compounds. London occurs mainly between nonpolar molecules and is a subtype of van der Waals forces. And in the figure, if electrons carried by the molecule are thought of as a cloud in motion, for a very short period of time, the electron cloud becomes such that temporarily one side of the molecule is charged with a negative charge, and the other side is charged with a positive charge. Continuum van der Waals forces or interactions, and the second type is dipole-dipole forces, which arise when two dipolar molecules interact with each other in space. And they are similar to London dispersion forces, but they occur in molecules that are permanently polar and in molecules that are momentarily polar. Dipole-dipole interactions are the attractive forces between the permanent dipoles of two polar molecules. An electrostatic attraction between opposite poles of molecules. When this occurs, the partially negative part of one polar molecule is attracted to the partially positive part of the second polar molecule as seen in the figure. And both attractive and repulsive dipole-dipole interactions occur in a liquid substance with many molecules. And here the black dot lines represent repulsion and the red dot lines represent attraction. Ion dipole forces or interactions. An ion dipole force is an attractive force resulting from the electrostatic attraction between an ion and a neutral molecule with a dipole. It is most encountered in solutions. It is particularly important for solutions of ionic compounds in polar liquids. And the positive ion, which is a cation, attracts the partially negative end of a neutral polar molecule. A negative ion attracts the partially positive end of a neutral polar molecule. The ion-dipole interaction becomes stronger as the charge on the ion increases, or as the magnitude of the dipole of the polar molecule increases. Here in this figure, you see the ion-dipole interaction between the water and sodium cation and the water chlorine anion in a sodium chloride solution. And as you see, the water molecules surround the chlorine ion by their hydrogen side, which is partially positive charge. And for sodium, the oxygen side surrounds the sodium. The oxygen side of water molecule surrounds the sodium, which oxygen is a partially negative charged part of water molecule. Hydrophobic interaction. Hydrophobic interactions describe the relationship between water and hydrophobic, low water-soluble molecules. Hydrophobic molecules are nonpolar molecules and usually have a long carbon chain that does not interact with water molecules. Mixing oil and water is a good example of this interaction. A common misconception is that water and oil do not mix because the van der Waals forces acting on both water and oil molecules are too weak. However, this is not the case. The behavior of an oil droplet in water is more related to the enthalpy and entropy of the reaction than to the intermolecular forces. Nonpolar substances such as oil molecules tend to clump together in water, and this ensures that the oil molecules have minimal contact with water. And here in this figure, as you see, nonpolar molecules depicted with the polygon, the pink or the red polygon, antipolar molecules with blue color spots. Nonpolar molecules or ensembles of molecules tend to associate with water molecules, as you see here in this part, to reduce the contact surface with neighboring water molecules. Hydrophobic interactions are relatively stronger than other weak intermolecular forces, and this depends on several factors. And the one is temperature. The strength of hydrophobic interactions increases as the temperature increases. However, at an extreme temperature, hydrophobic interactions will denaturate. Second factor is number of carbons in hydrophobic molecules. Molecules with the largest number of carbons will have the strongest hydrophobic interactions, as seen in fatty acids, which are the components of cell membrane. And the third one is shape of hydrophobic substances. Aliphatic organic molecules have stronger interactions than aromatic compounds. Branches in the carbon chain will reduce the hydrophobic effect of that molecule, and the linear carbon chain can produce the largest hydrophobic interactions because, for example, a hydrophobic chain, look at this one, or an aromatic compound such as the benzene, for example, and as you see, the aliphatic organic molecules, which has a longer straight chain structure, occupy large space, but for the aromatic occupy lesser space. And also this pattern or this molecular pattern create steric hindrance. So it is more difficult for two hydrophobes to have very close interaction with each other to minimize their contact with water. Hydrophobic interactions are crucial for protein folding. They play a key role in keeping a protein stable and biologically active. With this interaction, the protein surface area and unwanted interaction with water are reduced, as seen in isolated water, which carry both hydrophobic and hydrophilic regions. And here in the protein aqueous solution, which is a folded protein, the hydrophobic regions locates or stay away from water or minimize contact to water. Besides proteins, there are many other biological substances in which hydrophobic interactions play an important role for the survival and function of every single cell of our body. And a good example is the phospholipids, which they contain fatty acids and the components of cell membranes. And the last content of this topic is the coordination chemistry and metal complexes. Coordination chemistry is an important branch of chemistry founded by Alfred Werner and has a history of about 130 years. It is one of the fastest and most important developing branches of inorganic chemistry. Coordination chemistry, which has a very wide field, is essentially a field where coordination compounds or metal complexes and ligands are studied. Under the title of Coordination Chemistry and Metal Complexes, it is aimed to give brief information about the subject and metal complexes in biological systems. And before passing to next slide, I want to give brief information also about the Alfred Werner, and he was the first inorganic chemist to win the Nobel Prize and the only one before 1973. Coordination compounds or coordination complexes are molecules or complexes that form centers of one or more metal ions to ligands, defined as atoms, ions, or molecules that donate electrons to the metal. In other words, in complex structures, a metal ion acting as an electron acceptor is located in the center, while an electron donor, defined as a ligand, is attached to this central metal ion, and these structures are called metal complexes. And these complexes can be neutral or charged. When the complex is charged, it is stabilized by neighboring counter ions. A complex ion has a metal ion at its center and a series of other molecules or ions surrounding it. And these can be thought of as being connected to the central ion by coordinated covalent bonds. And for the information about the coordinated covalent bonds, you can look to my website BiyokimyaVET. And in some cases, the bond is actually more complex than. Coordination compounds, due to their various properties such as reactivity, magnetism, molecular structure, etc., are currently used in polymer technology, understanding of biological systems, medical use, drug development, that's so in industry. Ligands are ions or neutral molecules that bind to a central metal atom or ion. A metal ion in solution is not in isolation, but in combination with ligands, such as solvent molecules or simple ions, or chelating groups to form coordination complexes. And these complexes contain a central atom or ion, usually a transition metal, and a cluster of ions or neutral molecules surrounding it. Ligands can be anions, cations, or neutral molecules, and can also be characterized as single-toothed, which we call them monodentate, two-toothed, tridentate, three-toothed, tridentate, four-toothed, tetradentate, multi-toothed, polydentate, etc., from the concept of teeth, which in Latin dent. This is because the ligands bind the metal ion in a way that resembles the way teeth bite into food, such as the number, shape, and angle of the biting teeth. Another analogy is that the ligand binds the central particle in the biting position, like the teeth of a pilliers. And eta-ethylene tetraacetic acid is a good example of a multifined ligand. The eta-calcium complex with calcium is used to prevent blood samples from clotting. So eta is a good example of a multidentate ligand. The eta-calcium complex of calcium is used to prevent blood samples from clotting. And especially choose the purple color uh, in giving this information to you because the tubes, blood collecting tubes, containing eta as an anticoagulant matter because the blood clotting in terminology we call it's coagulation. So anticoagulant means blood coagulation preventing matter. And in general, the blood collecting tubes having eta as an anticoagulant have lavender tube cap or purple tube cap. The definition of ligand is used with different meanings in chemistry and biochemistry. In chemistry, it is defined as an atom, ion, or a functional group that donates one or more electrons to one or more central atoms or ions through a coordinated covalent bond, while in biochemistry, it is defined as an extracellular compound that binds mainly to receptors. So this is a kind of footnote for you. Chelation is a process in which a multivalent ligand binds to a metal ion to form a ring, and the resulting complex is called a chelate or chelate complex. Chelate complexes are a special form of metal complexes formed by ring-shaped compounds, and the adjective chelate derived from the large claw or chelia of the lobster or other crustaceans, and is proposed for the caliper-like groups that function as two connecting units and attach to the central atom, ultimately forming heterocyclic rings. Chelating ligands or chelators have a higher affinity for metal ions than monodent ligands. ETA is a good example again of a chelating ligand. Chelators are usually organic compounds. Special forms of nitrogen, oxygen, and sulfur atoms such as ammonia, hydroxyl group, or sulfitryl group act as a free electron carriers in the formation of the chelate complex. And the formation of a chelate depends on the size and electron configuration of the central cation. Therefore, only certain cations fit the teeth of a chelate formers, and chelators have a high selectivity. And here you see the popular and the critical components of the life which carry metal complex structures. And here you see the heme, which will also have a porphyrin ring, and this is a part of hemoglobin or hemoglobin structure contain heme, which the iron binds oxygen. And hemoglobin naturally occurring in biological system as well as the other ones. And the most important example is the iron porphyrin complex found in the structure of red blood cells, erythrocytes, which transport oxygen, which is essential for metabolic processes in tissues in aerobic living beings. And cytochrome C here you see, and the cytochrome A, and other molecules carrying the porphyrin ring, the colorful chelate complexes with iron or copper as the central particle, located in the mitochondria. They differ significantly from heme in that the valence of iron in their structure changes, but they do not lose their effect. The basis of the function of cytochromes is also mostly due to the change in the valence of iron in their structure. And the last example is the cobalamin, vitamin B12, biologically important chelate complex which carry cobalt. It contains cobalt as the central cation. Also, there are artificial chelators which are important. When artificial chelating agents are added to the living organism, they react with more or less existing metal cations. And these substances mask and neutralize the metal cations by chelate formation, and the chelate can be extracted from the organism. Both effects can be used for medical purposes. In this way, metallic poisons and radioactive substances which are harmful to the body can be detoxified. The development of artificial chelators is an important field of study. And now we reach the end of the topic. And here there are some references both in Turkish and English for further reading. The next topic is going to be matter and their features. For more about biochemistry, clinical biochemistry, and also the laboratory sciences, you can visit the website biyokimya.vet and also the Instagram account biyokimya.vet. Do not forget to subscribe, click on thumbs up, and open notifications for further news. And eat, study biochemistry, sleep, and repeat. See you in our next topic. Goodbye.